طيب بسم الله والصلاة والسلام على رسول الله. السلام عليكم ورحمة الله وبركاته. حياكم الله جميعا. بس أكدوا لي إذا الصوت واضح. طيب أوكي تمام. طيب هذه الدورة مقدمة من مركز الموهبة والإبداع بعنوان الروبوت. أتوقع يعني أغلبكم سجل هو عارف إيش الدورة هذه، عن إيش تتكلم بالضبط. الدورة هذه بشكل يعني مختصر تهدف إلى تغطية أبسط مهارات الروبوت، من تشغيل، من تحكم، من توجيه، ومن إدراك والذكاء. طبعا مقدم الدورة الدكتور محمد بلال، هو دكتور وأستاذ مشرف في قسم الهندسة الكهربائية، كما جدير بالذكر أنه أشرف على الفريق الحاصل على المركز السابع عالميا في مسابقة أولمبياد الروبوت. دكتور عنده علم جدا كبير. ملاحظات بسيطة قبل ما نبدأ بس. الأسئلة حبذا تكون في نهاية اللقاء، فإذا عندك سؤال يا ليت تكتبه وبإذن الله حنجاوب عليه في نهاية اللقاء، فلا تستعجل. طبعا بالنسبة لموضوع الشهادات والنقاط حتكون برضو في نهاية اللقاء، بينزل لكم رابط تسجيل تسجل فيه، ومن هناك نقدر نسجل لك النقاط وبإذن الله نسجل الشهادة. طيب هذه مقدمة بسيطة. نترك المايك للدكتور محمد. طبعا نسيت أذكر أنه الدورة بتكون باللغة الإنجليزية لأنه الدكتور ما يتكلم العربي. So yeah, this is a quick brief. Now you can start, Dr. Muhammad.
Assalamu alaikum wa rahmatullah. Thank you for the introduction, and let's formally start with our session today. So initially the title was just the robots, but now then I made took some liberty to add a few keywords here to make it a bit more meaningful. So today, inshallah, we are going to talk about robotics in general, which is the field of how to make robots, how to operate them, how to produce them. And within this field, there are currently three major problems or three major fields that you could work in. So the first is the motion. That's obvious with whenever the word robot comes to mind. So the motion is the first thing that we think of. And then perception and learning, these are more advanced topics. If you want your robots to be more advanced, more intelligent looking, or more sophisticated, so then they should be able to do a lot more than just simple motion. So let's start. Let's dig deeper. So the thing is, the robots, they are actually not a new concept. And as long as ago as 1720s, people were making robots, although they were not electric robots. They did not use electricity to run. But this very famous robot, which was back then called an automaton, and specifically a writer automaton. This was developed by a watchmaker in Switzerland. So, you know, watchmakers, they were very exceptionally good at making dials and very precise movement of dials, because the clocks require, of course, very precise movement. So this particular robot or automaton, this was able to write signatures mostly on a piece of paper. And if you are interested in watching the whole thing, so there is a short BBC documentary on it. So I've provided the link, or you could just search on Google. And this is a very interesting short documentary that if you're interested in robots, so that would definitely you will like that. So the thing is, the concepts or the fascination with machines that could operate like humans, that is not new. And one important thing to note here is that this automaton, this was made like a human, although it is only meant to sign and it does not do any other thing like humans do. But the fascination with making a human-like machine which could do human-like operations, that is not new. So people have always wanted to build robots. But fortunately, in 2021, we now have a lot of resources and we can make a lot more sophisticated robots, intelligent robots, and powerful robots. So about talking about the fascination, science fiction is always the first place where you look for where humans have their eyes set. So so if you have been following the robots in science fiction, so you will probably notice something, and that is the level of intelligence and sophistication. So as we are moving more and more towards intelligent systems, so we have started seeing robots in the media and in science fiction which are as close to human appearance as possible. And earlier so for instance, in Star Wars, the first robot that was, although very capable, but it did not even speak like humans. And although it did show some intelligence, but we settled with that. But now that robot is far from what we need or what we want. So for example, the Sophia robot, which is a reality, not just science fiction. It is almost like a human. So we as humans want a companion or something, a helper, which not only helps, which not only understands us completely, but also look like us. So that is this fascination. Although if you have a machine that does not look like humans, so and if it is doing all the jobs, so still it should be fine. But talking about fascination, this is what we want. So as I was talking just about the Sophia robot, so it is not only intelligent in the sense that it can sense its environment and do a lot of things. It is also human-like, and it is capable of expressing emotions. And in fact, the very purpose of building this robot is emotions, expressing emotions, understanding language, creating sentences, and doing a meaningful conversation. So the purpose of this robot is entirely different. It is just for it is not for doing your ordinary chores at homes or offices, but for an entirely different purpose. On the other hand, some very sophisticated robots from Boston Dynamics, or recently the SoftBank from Japan, they have made some very sturdy robots, which again look like not some of them also look like humans, but many of them also look like robots. So for instance, the one GIF that you're seeing on the right, that's their famous dog. So it's very extremely capable in terms of balancing, agility, and environment perception. So very capable robot, and has some very sophisticated military applications. And so this was built primarily for operating in rugged environments. So these robots, they are not meant to be used in your homes, offices, for ordinary jobs. So although we call them the most sophisticated robots, the modern robots, but the thing is, you cannot, although they are quite sophisticated, you cannot still use them in your homes. They cannot help you in your kitchen. They cannot help you clean your house as good as a human helper would do. Same goes in offices. These robots, they will not carry papers from one place to the other, bring out papers from one shelf, put them into another. So those kind of jobs, although they look boring, they do not, maybe we are not fascinated by that, but we are still very far off from those kind of operations. So although these robots are impressive, but they are very far off from what a human is capable of doing. So this talk is mostly about we have now set the standard is too high. Sophia robot, extremely capable. Boston Dynamics robot, again extremely capable. So these are made in very sophisticated labs, lot of resources, teams of hundreds of people. So the thing is, as engineers working independently or in smaller teams or in areas where the robotics is not the main specialty, so what we could do about it. So in this talk, we will inshallah discuss the key ideas, the key skills that we need to acquire before we can make some meaningful robots. And as I mentioned earlier, even though these robots are very specialized, they are still not up to the mark. And probably some very dull robots, very simple robots. We could make those and they could help us a lot in our homes and offices. So they will not be exactly human-like maybe, but they could help us a lot in our daily life. So that's the goal here. We are not looking forward to make some very fancy looking robots, but looking forward to making robots that help us in our daily lives. So the first thing, as I mentioned in the very first slide, there are three things that you have to know about. So first is, of course, the motion. A robot will be called a robot only if it moves. So the first thing is, among the basics, actuation. That's the movement. So actuation, when, of course, the movement is done through a motor or a mechanical part or anything like that. So that is what we call, in the jargon, we call it the actuation. And then that simple motion is not enough, because we have motors at homes, fans, which simple do you turn on the switch and it starts moving. So we are not looking for that kind of motion, simple, but we want some sophistication. We want it to move on command, and we want to move it precisely according to a pattern. So that is what will require sensing, control, and guidance. So this is where we want to make our robots to do very precise movement, not just repetitive, simple, circular, or linear motion, but something based on the external inputs. And then finally, we would want to impart intelligence into it, so that it maybe even without command, it should be able to do certain jobs. So for that, we will have to use concepts from computer vision, artificial intelligence, and machine learning, etc. And then finally, at the end of this talk, inshallah, we will look at some of the case studies that we did locally. So in order to show what could be done with limited resources, I'm talking about resources less than hundreds of thousands of dollars. So we will see what we could do, and as smaller teams in universities and as engineers. So let's start dissecting a robot. Let's go inside. Let's see what makes a robot a robot. So the first thing is the actuation, the basics. So you can appreciate that there are different types of motion. So simple circular motion will takes a car from place A to place B. And then we have linear motion. Linear motion helps you move things from one place to the other in a linear fashion. And then you could have some very sophisticated, you would want a sophisticated motion. For example, in a printer, you need to put ink at a special place exactly where you want it. So very sophisticated motion there. And then grabbing a human-like hand for grabbing things, or an industrial grabber for moving heavy objects. So all of these, they require different kinds of motion. So each type of motion requires a different type of motor. So I will just briefly go over a few types of motor that you have to use in order to achieve those goals. For example, the continuous rotary motion, everybody is familiar with DC motors. And again, DC motors, this is, although I have lumped everything up in this small topic, DC motors, but there are just too many varieties there. So DC motors have multiple types there. Some of them are geared to give you extra torque. Some of them don't have gears to give you a lot of speed. So there are just too many options out there. So once you go deeper into that, you will come to know. And then another purpose of the motors, as we saw, it was the precise motion. You would want the motor to go from one place to the other, or you would want your hand to move from one place to the other. And maybe you would want it to move by a millimeter precision, for instance. So that would mean you need to measure the amount of displacement that a motor has made. So for that, we would need these position encoders. So in the previous slide, we saw that we add gears to the motors to add the torque. And then we add position encoders into the motors so that we would also know that how much the motor has moved, so that we could make the motion precise as well. So precision and torque, these are the two things that we want our motors to have. And then we would also want to of course, the most basic requirement is that we should be able to control the speed of the of the motors as well. So this is one very simple diagram. I first had thought that I would probably not include any circuits here, maybe because not to make this presentation too heavy or too boring, but anyway, I put that. So if you are looking for a quick and dirty job, want to make a very quick robot out of the motors that are commonly available, so maybe you could do something like this. So this is a very basic direction control system, and that uses what we call the H bridge. So H bridge is simply a set of switches, you would say. So you open and close a set of switches and you could control the direction of that. So for example, in this case here, you can see that these two switches have been closed, and this allows the current to follow this path. Positive is here and the negative is here, and the motor runs in one direction. So maybe this positive here, it means that the motor will probably take a clockwise turn. And then if you do the opposite, you close the opposite end of switches, then the polarity of the voltage changes. You see, notice the positive sign is here, negative is here, and now the motor will start moving in the other direction. So that's one of the very basic direction control circuit that you would need. So again, there is just too many relevant topics here that are probably outside the scope of this short presentation. So I would not go into further circuit details. The purpose of, or the lesson from this slide here, is that if you want to go into the details of actually hooking up motors and you would want to do a design from scratch, then you should be willing to deal with some of the power electronics as well, because as the motors become bigger and bigger, they will require more and more sophisticated or more powerful electronics as well to drive them. So this small part that I have just mentioned here, this is only for making very small cars, or you would say maybe the toy cars. So if you want a meaningful load to be carried, then you would be looking for something more advanced. So basic control is as simple as that. We already have a lot of power electronic circuit available with us, and they can help you make the robot go from one place to the other if you don't want any sophistication. But of course, we are looking for sophistication, so let's add to this a bit more. So we saw that we could maybe change the direction of the motors. So another related concept, using the same circuit or a small variation of that, we could use something that we call the pulse width modulation. So what's that? Essentially, this is a voltage pulse. So if you notice here, there are 3 different pulse shapes being shown here. So notice there is a number associated with each one of them. So first one is 50%, the second one is 75%, and the third is 25%. So the difference between 50, 75, 25 is the width of this pulse. So you see, this is 50% of the time it is high, and then you see 50% of the time it is low. And then this one, 75% of the time this is high, and 25% of the time it is low. And similarly here, 25% of the time it is high, and 75% of the time that's low. So this is what we call the pulse width modulation, and this helps us control the speed of the motor. And how does that happen? Because if you take the average of the average voltage, by average we mean since this is 50% on and 50% off, so you could say that the average voltage is 50%. And here the average voltage is 75%. And then here the average voltage is 25%. So this average voltage basically controls the speed of the motor. So using a very simple control circuit, you could change the speed of any given motor. So again, I am not going to dig deeper into that, because today we are going to look at things from a bird's eye view, from a bigger perspective, and not going into the tiny details. But anyway, this I thought that maybe we should mention that the basics of the robots, that is speed control, direction control, and simpler motor control, these problems, they have been solved many years ago. So the robots, or the essential parts of the robots, they have been here for many decades now. So we have these circuits available with us. Power electronics was pretty advanced even 2-3 decades ago as well. But what has driven the revolution now is the intelligence. So let's quickly move on to the topics where we impart the intelligence to robots. So this is just using the same circuit that I had shown you earlier. You could not only change the direction of the motors, but also control the speed of them. And then using the same type of the pulse shape that I was showing you here, there is a name for that, and that's the pulse width modulation. Actually, I think this was written here. Yes. So PWM is pulse width modulation. So what does that mean? Pulse, we are changing the pulse of the signal. So hence the name pulse. And since we are changing the width of that, so hence the W here. And modulation means changing. So we are changing the pulse width. So this is how the motor is being controlled. Now here, in a different type of motor, this is an entirely different type of motor. Although it is still DC, it works on DC current, but its purpose is to not move continuously, but to move to a particular move by a particular angle. So how do we do that? Again, surprisingly, using the same type of pulse width. So for example, if we lower the duty cycle of the same width of the same signal, maybe 25% here, so it will move to maybe this position here. Let's go. So this position here, this corresponds to 25%. And this position, this corresponds to 50%. And then this one is probably corresponds to 75% or something. So the same type of signaling, but it is driving an entirely different type of motor. So this type of motor you could use if you want to maybe build a robotic hand, which can move by a very precise movement. So you hook up multiple of these and you can have a sophisticated design like this one. You see, this is an industrial motor, and it is using 3 or 4 such motors. Not, of course, this much smaller in size, bigger motors, more capable with more torque, but the control is precise. And the control is somewhat similar to this pulse width modulation. So you hook up multiple of these and you can make a very sophisticated robotic hand as well. So we are sort of, we have seen that motors can give us some torque. We can move them precisely. We can move them in either directions. And these gears help us carry a lot of weight as well. So these are the motors that are already available. And in 2021, we have a lot of very good options available in the market as well. So you could very cheaply buy some of the very capable motors, capable in terms of carrying the torque and speed and agility and the ease to control. So all of these, they are pretty cheaply available in the market. And this, to be frank, this is a very exciting time to be in robotics in this time, because you could, even if you are an engineer with low resources, you could build very interesting robots using this. And then another thing that we could do with the motors is, although we saw that the previous motor, the servo motor, that could do precise motion, but sometimes we want even more precise motion, maybe in the order of millimeters. So that is what we have. For this, we have motors that are called the stepper motors. So stepper motor control is a bit more precise. It requires multiple pulses. And if you are familiar with the 3D printers or even the normal printers that we have, they make use of such motors, because 3D printers and your normal paper printing printers, they require very sophisticated control, because they are going to print either using plastic or using actual ink. So you would want them to make very precise movements there. So this is where we have stepper motors come into play. And generally stepper motors, they are although very precise, but they cannot carry a lot of torque here. So if you are looking for an application where you would want a high torque, so maybe you should use a geared motor, a servo motor, a normal DC geared motor. But if you're looking for very, very precise motion, then this is the motor that you should be looking at. And again, the position control, it requires multiple pulses, and they could be a bit more harder to control. So again, there are multiple drivers, hardware drivers available in the market very cheaply, that take care of most of these intermediate steps for you. So this is some further details of the same thing. So you can see that this requires, in order to move it very precisely in the order of millimeters, you require a very sophisticated set of pulses as input. So we have seen the basics of the motors. So 3 types of motors to impart speed, torque, or precision. So this is the summary of these 3. Then we would, of course, want our robots to feel the environment. So in order to feel the environment, to make some basic decisions, they would want to make use of some sensors. So again, the sensors can be some very simple ones. For example, some sensors, they can sense the distance using an ultrasonic sensor. For example, maybe some of you are already familiar with this. So this ultrasonic sensor, it can tell you, using the equilocation principle, it can sense what is the distance between the sensor and the nearest obstacle. So this is a very simple sensor, very easy to use, very, again, commonly available, but of course it has some limitations. For example, if the object is at an angle, sometimes if the angle is too sharp, maybe it will not be able to detect that. And secondly, it does not work on all kinds of materials. So for example, on harder surfaces, it will work really well, but on softer surfaces like clothes or foam, it may not give you either no reading at all or some very noisy data. Then you would maybe want to sense the light. Light sensors are available, very cheaply available. And then we have position encoders, positions. So how do we sense the position? All of us are familiar with GPS for outdoor positioning. So if your robot is moving outdoors, then sensing your position can be very cheaply and very accurately done through a GPS. But if you are indoors, then this presents some more challenges. So remember, we were discussing something about the encoders inside the motors. So sometimes those encoders inside the motor, they can help you determine the position of the robot. But of course, they are much less precise than the GPS. So for that, we will have to maybe use some other sensors. And then lastly, the image, or more precisely, we should actually say video, because we would want a continuous stream of images, and that would constitute a video. So in recent years, video or images, they have taken over the robotics field by storm. And a lot of these things here, the distance measurement, light, of course, and the position, all of these 3 and much more can be done only through one sensor, and that is your video camera. So that's why sometimes computer vision, or which is the field to process live images or videos, this is sometimes written synonymously as the robotics. So it is understood that if you are, for example, working in robotics, and not just very simple robots, some meaningful robots, then you should automatically know a lot about computer vision. So what's computer vision? Computer vision is dealing with the images. And why is that important? Because as we have just mentioned, images contain a lot of clues that could help us get rid of a lot of other sensors. And even if we don't entirely get rid of the other sensors, this information can help us be more accurate in our sensing. And then, of course, all of this has to be processed in the microprocessor. A smaller microprocessor, if your robot is small, or if your robot is big enough, then we could have a very big capable microprocessor as well. And then that, of course, necessitates the software development part. So you see very quickly, when you make your robots, which can do some even some basic intelligent stuff, you will have to go into, you will have to learn at least 2 or 3 skills. So simple motion or simple actuation, that would require you to make use of, to know a few things about the power electronics. So power electronics is, you could say, it will get you there. So if you know power electronics, or know at least how to deal with off-the-shelf ready-made power electronics components, so you can solve this problem of the motion. But as soon as you would want to impart some intelligence into your robot through sensing and making some intelligent control, then you will have to very quickly develop some more skills as well. So first skill is computer vision, and we will see shortly what other skills are required, and that requires you to write a lot of software as well. And when it comes to running the software, so we are not looking for ordinary computers. They are specialized compute processors. Sometimes we call them embedded systems. So that is a different type of electronics. This is not power electronics, but this is this electronics is embedded electronics. So 3 skills if you want to at least make a robot that is intelligent enough. Not too intelligent still, but if you want some meaningful intelligence, so at least 3 skills are required until this stage. So if you would want a more sophisticated control, for example, now this one is a simple line following robot. So many of you probably have seen a lot of videos and maybe even built such kind of robots. So if you have done it yourself, you know that even if you would want your robot to follow a simple line that has been drawn on the floor, that requires a lot of things. So this simple robot, it is making use of some very basic power electronics, of course, to move the motors. And then there is a small microcontroller here. So you have to write a piece of code there as well. And then it has at least one sensor. That's a light sensor mostly. So a light sensor is here. And even if you put everything here, so on top of it, you have to write the software, the algorithm. And you know, even this simple kind of line following application, you have a variety of choices for the algorithms. You could do a simple on-off control. How would that work? On-off means that your robot turns left, and if tries to go off the line, then you start turning right. And then again, if it starts going off the line, then you turn left. So you just keep on turning left, right, and that would be a simple on-off control. But you know that control is horrible. This will work only for very small robots, and if you try to make it slightly bigger robot, or you would want a smoother motion path, then this is not going to work. So in that case, we would want at least a PID controller. So going from the basic to intermediate, this PID controller, those of you who have taken their control system courses, maybe they are already familiar with that. So this is a much better controller than the PID one. But quickly we have added another skill to our required number of skills. So that is the basic control. So you would know what is actually PID and how would that come into play when you have the sensory data coming from this light sensor. So this sensor is telling you a rough position of the robot. So how you use that inside a PID controller to make this motion smoother. And this is still an intermediate level algorithm. You could also use of some very advanced control as well. One example of that is the fractional controller. That's one example. Then there are sliding mode controllers, and so this is an entirely different, you could say, field there. So most of the times, robotics people, they generally settle with this PID controller, and then there are some ready-made solutions available. These algorithms, they have been implemented as software libraries. So people just very quickly use those libraries. But even to use those libraries, you have to be at least a bit more aware of what a PID controller is and what should be the inputs and outputs to that. So this was actually a very simple example, the simplest kind of robot that you could probably build. On the right side here, we have what we call the inverted pendulum. This is considered a fairly complex problem. So this inverted pendulum, what it is trying to do, actually, it is more complex than that. It is not just an inverted pendulum. It has actually 3 legs. You see, red, green, and blue, they are 3 different parts. So a simple inverted pendulum has only one of them. So it is trying to balance all 3 of them. And you see, the only motion that it can do is this motion, the translation motion. And using that and some sensors that it has, so all these 3 legs, they would have sensors. And those sensors are telling the controller that what is the position of each one of these legs. And then based on that position, it is trying to balance it. But the remarkable thing here is that it has only one available motion, and that is just translation. So here, this problem could, strictly speaking, be also solved through PID. So PID is actually a very, you could say, a universal algorithm that is very widely used in robotics application. Okay, so actually there are a few questions there maybe, but I think it's best if we keep the question and answer sessions towards the end. Okay, so what's next? You have a very basic kind of motion. You know how to make the motor. So you would probably have sensed that this motor here, this is probably a geared motor which can move sideways. And these motors, again, actually there are no motors here. These are only the sensors. So in this application, this is just one motor and some sensors here. And these are position sensors. These are the tilt sensors. Tilt sensors, they tell you what is the orientation or angle of various parts. So this is another type of sensors that you could add to your list. The tilt sensor is just like how your phone determines your smartphone can change the screen from landscape to portrait. So how does it do that? It has tilt sensor inside, so it knows which way you are holding your phone. So same kind of tilt sensors. Now they are some 20 years ago, maybe they were very hard to come by, but nowadays, even the cheapest of smartphones, they have these sensors. So they are very commonly available nowadays. And people routinely use them in their robotics projects. Okay, so we have seen now you can move the motors, you can move them precisely, you can move them in any way that you would want, but now you would, so that was the control, but now you would want them to accomplish a bigger task. For example, if you have this car, autonomous car, you would want it to move from place A to place B outside. So for that, of course, you need to run the motors. Of course, that's the given. So you will have to do that, but not just that. On top of it, you have to change the direction of the steering wheel. You have to change the speed of the car, and so on. So you see, this is the example that you are seeing here. This is a simulator, and this simulator has been made to for people who would want to work on autonomous car projects. So if you do not have access to an actual car and you do not want to work on building a car for yourself, a smaller car even, involving motors and electronics and all that, and you would only want to experiment with the guidance and advanced control, so you do not want to bother yourself with power electronics and such stuff, so then you could do things in simulation as well. So that is one aspect of it, and that is also, once you run your algorithms here in the simulation mode, then you could make your robots have a higher purpose as well. For example, going from one place to the other and also following the path, and the path in this case is the road, and then determining when to take the exit from a given road, how to take the turn, and then once you reach the place, then how to stop. So these kind of things, they are the advanced controls. So they are on top of the basic motor control, and we put them under the title guidance. So we started with simple motion. That simple motion is simply direction control, speed control, and then if you want to control how that motion should be controlled, based on what. So for that you need sensing. We saw a few sensors, and very quickly that involves some control, because simple on-off control does not work. You will have to use at least a PID, and most of the robotics project actually use PID, because although it is an intermediate level control, it is quite sophisticated, and it works for most robotics projects. So once you have that control over your motors, then of course your robot will ask, okay, I can move precisely, I can move with certain speed, but now what should I do? So then you guide it. Then you say, okay, now your purpose is go from this place to the other place, and maybe don't hit the objects along the way. So that guidance, now that could involve some more sensors. So for example, in an actual missile, the actuator is a simple motor, sometimes a rocket or something, and then you are controlling the actuator through sensing. So you are maintaining the position, maintaining the attitude, speed, and the height from maybe the ground as well. But then you have to guide the missile, so, or the rocket or aeroplane or whatever that is. So guidance is on top of these basic level controls, and they might require some more sophisticated sensors. So position is important. Position was important for simple actuator control as well, but in guidance this is also important. The speed, again, actuator control also requires the speed. This control requires that speed, but the guidance also has that particular, it will make use of that sensor here as well. And then air temperature and air speed, maybe they are not very meaningful for the actuator and the control part, but maybe the guidance will have to make use of these sensors to make some certain decisions. So for example, if the air temperature is too high, so maybe you would want your rocket or your airplane to climb higher, or maybe climb down, so because maybe the electronics cannot work at that temperature. Or if the speed is too high, at lower altitude. So maybe you would want to go higher up so that the airspeed is lower and there is less resistance. So guidance has its own set of algorithms and sensors maybe. And then once you have the guidance, so you know going from one place to the other, then you would want some more sensory data and maybe even replace the human operator and make it fully autonomous. So you see now this Boston Dynamics dog, what is going on here? While it goes from here to here, this is place A, this is place B. So actuator is moving, and there is not one actuator, there are multiple actuators. So this is not a rotary type of legs. So you can guess that these motors, they are probably a lot like the servo motors that we discussed. So servo motors, remember, they used some PWM signals to move by an angle. So it moves, so at 25 degree, maybe it maybe points here, then at 50 degrees it points here, and then maybe 75 degrees it points there, and then it moves like this back and forth. So it's like the movement of your elbows or movement of your legs, and same kind of information is there. So I'm not saying that this robot actually uses the servo motor, but what I'm saying here is that the motion is somewhat what you would want to have. So if you would want some motion like that, so servo motor could do that. And in fact, if you search online on AliExpress and some very cheap sites, you would find that people have actually implemented a replica of this robot using servo motors. So anyway, actuator is motors, and there are multiple of these, not just one. There are 4 legs, and each leg has at least 3 or 4 servo motors. So 12 motors are different. All of them are being controlled here, and their position is being controlled here, the actuator control. And then the higher purpose is so that was the simple speed or position controller. Then you have the control, because now we have to move them by a given angle. So every time the decision is sent to a servo motor that move by exactly 15 degrees. So that's the task of this controller here, that okay, move by 15 degrees, but it does not know why am I being told to move to 15 degrees and why not 32 degrees. So it just follows the orders. So where is this command coming from? This command is coming from the guidance. So the guidance is telling it that, okay, we have to move from A to B. So in order to move from A to B, this servo motor has to move by 32 degrees first, and then the other motor has to move by 15 degrees. And when we couple all of these motion for different servo motors, then a path from A to B could be this motion along path A to B, this could be achieved. So that would be guidance. And then who is telling this guidance to go from A to B? So the actual purpose, higher purpose could be something else, maybe follow some, maybe this robot is trying to maybe mimic these people, that they are also, maybe it is racing along with them. So maybe that's the higher purpose, why they are going from, it is going from A to B. And then along the way, not just go from A to B, if there is an obstacle, it has to avoid that as well. So that is where the AI comes in. It has to now look for obstacles, and there could be multiple sensors there, but mostly it will have a camera there. That is, camera is looking for possible obstacles, and if there is an obstacle, so what kind of what is the jump that I have to do? So that jump will again go to from this AI supervisory control to the guidance. Okay, that we have reached a certain point and now jump. So the guidance will control the parameters for the control and actual, and eventually this will go to the actuator, the right pulses, a higher pulse to some servo motors, a lower pulse to another motor, and that will ultimately achieve the goal of jumping. This is another view of a similar robot. I think this is an older version of the same thing, but this shows a few sensors as well. So for example, this rotating sensor here at the top, that's a LiDAR. LiDAR is like a lot like the radar, but it uses lasers. So this is mostly used for detecting obstacles. And then a person here, they try to throw this robot off its track, but it doesn't. So you can imagine that there are a lot of tilt sensors inside. So tilt sensors, they are part of this control. So control, one of the objectives of the control is to make the robot stable. It should not fall, because if it has fallen, then it has failed the control. So this decision that, okay, I have experienced some turbulence, so the control will sense and it will try to mitigate that. Because, you know, this movement here, this is not sensed by the AI, it is part of the control here. So some decisions have to be taken at the control level as well, but that decision is mostly low level. So that means the goal here is that maintain stance or just maintain upright position. So that's the low level control. So you see, very quickly, going from simple motor control to a very advanced application, various skills are involved, and the actual pulse that goes to the actual motor that is doing the job, that decision has been made at multiple levels. So why is a 25% pulse width being sent to this motor? That is a sum of that is dependent on a sum of or a variety of parameters, that variety of decisions that are taken at different levels: control level, the guidance level, or at the highest level, which is probably an AI. Okay, so we were mentioning this LiDAR. So this LiDAR here. So you may, so this is, sorry, I got muted. So right, so the LiDAR here, this is the kind of images that you get from the LiDAR. It's a 3D map of points. It's not, it looks like an actual image or actual video, but it's not an actual video. These are just the distances of various objects from the car, in this case, where the LiDAR has been attached. So this is the kind of video that it, or kind of LiDAR data that you get. So this is a very expensive 3D LiDAR. If you try to get even the cheapest of these, that is right now you could get for a minimum of 50,000 Saudi riyals. And that's the cheapest LiDAR, which probably does not give you this kind of picture, but a much more rough version of that. So LiDARs are expensive piece of equipment, and we don't have access to this mostly. But fortunately, a lot of those things, they could be done through cameras as well. So if you have been following the news, tech news, so you probably know that Tesla cars, they actually do not use LiDARs. They use cameras mostly. They also use radar, but not the LiDAR. On the other hand, Google is promoting, Google and other companies, they are extensively using LiDARs. So the point of mentioning this is that although LiDAR is gives you a very impressive picture of your surroundings, but a lot of these things could be done through the cameras as well. And that's why computer vision, as I mentioned before, computer vision is sometimes, if you are working in robotics, so people automatically assume that you know a lot about computer vision, because these days, without knowing anything about computer vision, you cannot do a lot in robotics. So this is one example of what the cameras can do. So you have live pictures, and then using computer vision techniques combined with machine learning techniques or artificial intelligence techniques, you could detect various objects. So you would know if a car is in front of you or a person is in front of you or it is just empty road. So a lot of the information that is here that could be attained through a simple camera as well. And then not just that, we could do what is being shown here, that is segmentation. So we'll actually come to that later in a later slide as well, but using computer vision techniques, we could actually know which part of the image is the road, which part of the image is the trees or other cars or people, and so on. So that could help us in navigating or finding our way without hitting anything. And then we could do all sort of other fancy stuff with computer vision as well. Okay, so we have seen that motion is actually nowadays maybe the least of our troubles, because they are, you could say this is a solved problem. If you want to move a robot from in a certain way, there are ready-made motors, ready-made electronics, and ready-made, a lot of libraries are, software libraries are also there. So that is probably the least of your troubles. Even the control systems, PID control and all, they are solved problems. Maybe you will not have to spend a lot of time in getting those right. But the environment perception, you know, our robots are now moving in a messy environment. Out in a road, on a road, the road is a messy environment. Anything could come up in the front. The road could have potholes. So, and then you have to keep track of your position, motion, and all that stuff as well. So this is what we call in robotics as the environment perception. A robot needs to know where exactly am I, what is the kind of environment I am in. And then within that environment, it has to localize itself that, okay, I'm exactly at this point in the map or an unknown place. So outside, you may think that GPS solves this problem. So with GPS and Google Map, probably you don't need to do much. But the problem is indoors. Once you are indoors, then a robot is blind. So a robot needs to know where exactly is it inside a building. So that poses some problems. And then the path planning, that, okay, you have to go from A to B. So what is the shortest path? What is the path that will consume probably the shortest time, and so on. So we, in that slide, we actually looked at a few things. In the scene understanding, for example, the object detection and localization, we saw that the cameras can do a very fine job combined with the machine learning approaches. Where is there a car in front of me? Is there a person in front of me? And where exactly is that person or the car? And segmentation, we saw that it could tell us where is the road, which part of the image is the road, which part of image is the sky, and so on. And then localization and mapping, again, we just discussed that outdoors, this is not much of a problem, thanks to GPS. But indoors, we have a lot of trouble. So there are certain algorithms that have been refined over the years. All of them, they are based on mostly your wheel encoders, which are inside your motors, and images and videos. So that's why computer vision, image processing, and machine learning, they have to play a bigger role in these kind of tasks. So that's why in robotics these days, machine learning is, so you could say that they are sort of synonymous. So machine learning, although it is an entirely different field than computer vision, earlier it was supposed to be, but now since machine learning uses so many of the computer vision stuff, or machine learning uses so many of the images, that sometimes people think that they are one and the same thing, but they are not. And then if you combine the robotics, so some people would automatically assume that if you are in robotics, so that means you are a machine learning expert as well and a computer vision expert as well. Although we have seen now that robotics is just not that. But recently, due to the advancements in computer vision and machine learning techniques, people have noticed that robotics can make use of a lot of computer vision machine learning stuff to make robotics systems more impressive. So that's why now a big part of robotics is about machine learning and computer vision. So object detection, I will just briefly go over these topics because they are related to computer vision and machine learning. They are not strictly speaking robotics, but robotics definitely makes use of this. So object detection is that within an image, you would want to see where an object of interest is. So for example, in the case of a robot that is moving outside, we would want to know whether there is a vehicle in sight or not, or maybe there is a person in the image or not, and sometimes also able to read the text, or maybe if the traffic signs or speed signs and so on. So that generally comes under the broad category of object detection. So this is a topic in computer vision as well as machine learning, and by extension, since robots can make use of the object detection, especially when you don't have a LiDAR. So if you have the LiDAR, as we have seen, it gives you a pretty good picture of what is ahead of you, but it does not tell you what exactly is that. So for example, it could tell you there is an object in front of you, but whether that is a person or a car, only an object detection inside an image processor could do that. So there are various algorithms there that you could maybe make use of. Again, this session is not about machine learning and computer vision, so I will just briefly mention that and we will pass. So this is what a robot should be able to do actually in real time. It should be able to see if this camera is in front of this robot, so it should be able to see what is going on. So this is about the environment perception. So if you see a lot of vehicles moving in front, so that means I am on the road and I have to be careful and I have to take care that I do not hit anyone. And if you are indoors, so then there will be in indoors there will be different kind of objects that could be detected. So a lot of algorithms and a lot of progress has been made there, and we have come actually quite far in this respect. And we have some very impressive algorithms in computer vision and machine learning. For example, a few of these, maybe if you just do a quick Google search, you will come up with these. So single shot detectors by Google MobileNet SSD, or You Look Only Once, YOLO, or RCNN. They are very fast and very accurate object detectors. They can tell you what kind of objects you are looking at, and a robot could make a good use of that. So you see, if you are seeing a lot of people, maybe you are indoors. If you are seeing a lot of vehicles, maybe you are outside. If you're seeing different kind of things, so that is about the perception of the environment. And this was the segmentation that I was talking about earlier. Other than the detection, segmentation is a bit more in detailed job. That means in the detection, you were only maybe putting rectangles around the objects. But here you are doing a pixel level job. You are saying that, okay, this whole yellow thing is the background, and then we have a cup with the boundaries and so on. So our machine learning algorithms have actually quite been successful in doing that as well. And that is extremely helpful for robots, especially that are moving outside. So they would know what part of the road is cleared, and so that they could continue their journey there. Like this, for instance. So a robot is taking picture like this, and after segmentation, the picture, actually this one probably belongs to this one here. So yes, please. So let's take a look at maybe this example. So you see, you are looking at, or the robot is taking this picture, and the output of the segmentation is this one. So this is color coded, and the road has been color coded with this color here. So the robot will know that, okay, this part of the picture is the road, and then it can move on. And then if the input is like this, so you see this picture here, the road has been color coded, and it has rightly identified a pothole as well. So you see there, the road is has a porthole here, and that porthole has been identified so that robot could maybe slow down there. And then not only that, it is also detecting the vehicles as well. So vehicles have also been detected. So this is about perception, and a driverless car could make good use of this information. And for the robots inside, if you want the robots to interact with the people around to follow some instructions, so again you could maybe make use of some hand gestures as well. So that is actually a simpler task, and computer vision has shown some remarkable progress in this aspect as well. Okay, so inside we were discussing that localization inside without GPS is a difficult job. So you could use a robot wheels to know where, so you could measure the turns of the wheels to know where you are, but that is not very accurate. So again, computer vision has done some marvelous jobs here. So you saw this video here. So a robot can take those individual pictures, and it can know that have I visited these places, so it can do a recognition job as well. So if you know that, okay, this place in the hallway, for example, is your designated 00 location, for instance. So after looking at the pictures, it will know that I am probably at location 00, and this probably location is maybe 100, 200 maybe. So by looking at this captured image, it would know that, okay, I'm at that location. So using cameras indoors with the known videos, so you could do a localization job as well. And similar thing could be done outside as well. So although outside GPS does a better job, but sometimes if you have poor GPS localization due to some it could happen due to various reasons. Sometimes when you have high-rise buildings, for example, then the GPS has very poor localization in narrow streets. There you could do the same thing. So visual place recognition, or using images to know the exact location, that is one place where again computer vision has done some good work. But of course you can appreciate that this is a difficult thing. Images can contain a lot of data, and the videos, there could be literally trillions of frames there, and processing through all of them, that can be difficult for smaller robots. So that's why this application is mostly for indoor robots in a known environment. So that the robot does not, the small computer that is on the robot, it doesn't have to do a lot of processing there. And then a related topic is the visual odometry. So we can know the rough place through image recognition, but using the cameras and the orientation of the camera from one frame to the other, we can also know how much the robot has moved, and if it has also maybe changed its orientation as well. So from this position in 3D to that position in 3D, that if you have a camera mounted on top of it, so by looking at the two different frames, it could tell how much it has moved. So that is called the odometry. So again, we could install these sensors in the motors as well. And motor sensors, they are pretty well, but they have a lot of errors as well. So visual odometry based only on the cameras, we could do the same thing. And when you combine this data with the wheel encoder data, then you have a much better estimate of your position and your speed and other such things. So all of these things related to position and mapping, they are for indoor environments where you do not have GPS. But of course, outside people have use this as well, because if it works indoors, nothing is stopping it from working outdoors as well. So here, for example, you see, this is the only thing that we are getting. This is the only sensor that this robot has. And what it is doing, you see, the car takes turns, and we are mapping this. We are mapping this accordingly by looking at the frames that, okay, there was a movement towards the left. So we now know that the car took a left turn here, and then took a slight turn towards the right, and so on. So all of this is entirely based on this camera frames. So you see, we are now making a full map of the whole thing. So this is an interesting area, and people have done a lot of work there. And this was actually done in this paper. These results are from this paper, which was almost 10 years ago. So people have made a lot of progress since then. But again, you must appreciate that this is not an easy thing to do on a small computer. It requires a lot of computing resources. So if you want to do something like this, you be prepared to get a bigger system there. Smaller robots cannot afford to have a small embedded system which could do this. And then this is the indoor environment again, a very similar concept. And here what is being done, the robot is carrying this camera to various places. And along the way, it is not only just noting the angles by which it is turning, but also, you see, on this case, it is also mapping it. It is building. So if you take this robot to all the places inside the floor of this building, for example, so it will eventually build the whole map of this. So that is what we call simultaneous localization and mapping. That means robot knows where is it exactly at this point, and also at the same time, it is also building a map of the building. So that's again a very interesting thing, a very compute intensive algorithm, but it can help robots that are especially that are intended to work indoors. So now we have seen that robotics is actually now a lot less about making the motors move, and now it is a lot more about analyzing perception, and mostly about computer vision and machine learning. So that's why now people think that robotics is about computer vision. And why? Because you saw from these previous examples that a lot of the things could be done in computer vision. So if you use a camera, a sophisticated camera, then you can get rid of a lot of other sensors. So you just have to only process one sensor, although that is difficult, but that helps solve a lot of problems in robotics. Skills you will have go over these. Common models and most in C++. Run them on your CPUs, computer, you could say.
نعتذر الدكتور محمد عنده مشكلة في الإنترنت. ثواني بإذن الله وحيرجع معنا. طيب نعتذر عن الانقطاع اللي صار. دكتور محمد جاته مشكلة في الإنترنت، حاليا رجع معنا. دكتور محمد, can you hear me?
Yes. So actually, sorry, I
Yeah,
had
it's
a
okay.
bad connection. So
You have the mic. Go ahead.
All right. So please tell me exactly where did you lose me? So did you get this point here when I was describing C++ or these Android devices?
No, it didn't show up. So I'd prefer if you can start from the beginning of this slide.
Okay, so from where? From this point?
Yeah.
All right, so about these software tools that you should be looking at. So one of the most important tool with respect to machine learning and is this TensorFlow. So in TensorFlow, the front end is Python. So if you're a fan of Python, then you could maybe just hop in and start writing your codes in Python, and then you are set. But if you are looking for faster implementation of your own algorithms, then I would recommend C++. So C++ is always the way to go if you are making your own algorithms and you want speed. So the good thing about TensorFlow is that now it is supported on multiple platforms. So on CPUs, GPUs, and TPU is, you could say, an advanced form of your GPUs. And not just that, you could deploy them on your Android devices, iOS as well. And not just that, again, smaller RISC-V embedded systems, you could actually deploy the tiny version of that. So there is a TensorFlow Lite version which can run on smaller devices as well. So if you are looking for computer vision, machine learning, so in general, not just for robotics, and you are interested in doing that for embedded systems, then you should look into that. So that's another skill that is nowadays almost necessary if you want to build robots. And this is one example there. So although not strictly speaking related to robotics, but to object recognition here. So for example, if you want to recognize objects, handwritten in numbers, for example. So this is one example there, and TensorFlow could help you build a model for that very quickly, so that you could recognize what number is being displayed on the camera right now, for example. PyTorch is another framework which is also catching up. Earlier, it was less known than TensorFlow, but nowadays PyTorch has also become quite prevalent. And this is actually provided by Facebook AI Group Fair, Facebook AI Research. So since Facebook is also spending a lot of resources and time on this, so PyTorch is also, you could say, a big player in this. But TensorFlow is probably more prevalent right now, as of now, than PyTorch. As for other tools and libraries, if you don't own a very capable GPU, maybe you could use online resources. For example, the Google Colab. So it allows you to use a lot of GPU and TPU resources even. And if you pay up, then a lot of resources are available for you. But again, these topics are more towards the machine learning side. But since machine learning is now considered a part of robotics, so I thought maybe we should use that. And then OpenCV, strictly speaking, this was the computer vision library. It was developed by Intel in somewhere around 99 or 98 maybe. So it was developed by Intel to do these computer vision tasks. But then, as I discussed previously as well, machine learning sort of encompassed everything, and machine learning made some very real progress in context of image processing and computer vision as well. So that's why now people think that computer vision is probably also the part of machine learning, although it's not true. So OpenCV library, which was for computer vision, it earlier did not have anything related to machine learning. it only used to do some basic and some advanced computer vision stuff. So you could do a lot of things there without using machine learning as well. But when you do things with machine learning, you can do it in a much better way. So that's why now machine learning is supported in OpenCV as well, but it does not allow you to build your own models. You can run machine learning models there, but it is not the place where if you are making your own models. So for that, you will have to go to TensorFlow or PyTorch and so on. And once you have trained those, then maybe you can come back here and run OpenCV there. And why is OpenCV important? Because it can run on smaller embedded systems, for example, Raspberry Pi or RISC-V devices. It can work really well. And since now it also has support for machine learning, so you could, if you have computer vision, if you have OpenCV on your smaller embedded systems, then you are actually fit to go. So you could do a lot of things there. So that's why I would recommend that if you are into robotics, then at least, even if you don't go into machine learning side, at least you should know what OpenCV is about, because camera is, now there is almost no robots without cameras. You should at least have one camera on your robots, if not more. And then on the other hand, we have MATLAB as well. MATLAB, the problem with MATLAB is the licensing. License is pretty expensive. But fortunately for us at university, KU provides the license for all the toolboxes. So if we make use of those license, then MATLAB helps you quickly build things and deploy them. And MATLAB encompasses OpenCV as well. So since OpenCV is license free, so MATLAB uses many. So it actually uses OpenCV in many of its algorithms as well. So MATLAB could help you do a lot of things here, and it could help you deploy on robots as well. Plus, it has full-fledged tutorials as well to make an end-to-end system. So MATLAB could get you going real quick. So if you have a knack for programming, and then you will find probably that if you write a code in MATLAB, that is probably it will take you less time to code than other languages. But the catch is, of course, the license, because if once you leave the university, you go someplace else and you do your own work, for example, so then since the license will not be there, and you will not be able to continue those things. But OpenCV, Python, C++, they are all free. Google Colab is also, some part of it is actually free. So if you are, you want to continue this journey license free, then I would say that you stay away from MATLAB. Then there is another dimension to robotics, and that is the robot operating system. So although the name says operating system, but this is not an operating system. This is actually a library. So I don't know exactly why do they call it operating system, but anyway, this is not an operating system. This is a library which you could install on Linux, Windows, any system that you would want, and you can also install it on smaller embedded systems. For example, Raspberry Pi, you could install it there, or Jetson Nano if you would want. So since this is supported on Linux, so all Linux-based systems, they are supported automatically. So what is ROS? ROS has a lot of, you could say, remember when we started talking about the robotics, we had earlier talked about the motor control, and then that was simple, you could say, power electronics. So on top of that, we had control, PIDs, guidance, and all of those things. So many of those things, guidance and control, algorithms, PID and everything, all of these, they have been implemented already in this ROS. So if you are not looking to reinvent the wheel or make your own course, then ROS has a lot of things already available in the form of a library. And this is a standard library. Many robotics interest group around the world in various universities, even in the industry, they use ROS. So a lot of open source material is available. So the thing with this is, however, that since this is a library, so you have to conform to their environment. So once you get there, then it is, you could say, in some ways it is limiting, and in some ways it is liberating. So in some ways it will help you. If you have installed this and you are working on in a ROS environment, then automatically you have a lot of things ready-made. So for example, the odometry part that we discussed, that is already there. You don't have to write anything. You just have to somehow understand how those modules are working, just make them connect to each other, then it works. And the good thing about ROS is that you can have multiple nodes. For example, you make one small node which is only connected to the camera, for example. That is one ROS node, ROS 1 maybe. And then another node which is connected to the motors, for example. So that's another node, ROS 2. And they could be connected through Ethernet or Wi-Fi. So you connect them through Wi-Fi or Ethernet, and then there could be multiple nodes. So you could have multiple systems working independently, and they will be all joined by the Ethernet. So ROS makes sense when you have a slightly bigger robot with multiple modules, and it needs to communicate with the base station as well, for example. So then it makes sense. Otherwise, again, this is an entirely different environment. Most of the programming is done in C++, but if you are not looking to make your own modules, then you could just use the open source ones and then just connect them, and your robot will start functioning. And it has a very good simulation environment as well. So ROS is one thing if you want to work on that. And a newer version of this is ROS 2. And ROS is important because it has been adopted by the industry as well. And some of the newer versions of autonomous cars or electric cars, they are looking, or they are eventually going to adopt ROS 2 in their system. So if you want to eventually work in the industry related to this, so then I would strongly suggest that you learn a few things about ROS. All right, so let's now quickly go over some of the stuff that we have done already at KAU, so that we know that some of the things that can be done with not too much trouble, even with very limited resources as well. So for example, the first thing that we did here, that was the SLAM, simultaneous localization mapping. So here, if you remember from the slides, the job is that we send this robot in an indoor environment, and robot does not know where it is and what kind of map is it. So it just moves around the building autonomously, and it builds a map for us, and then it moves around avoiding obstacles. So we used a simple LiDAR here. That's a 2D LiDAR. So 2D LiDARs, they are very cheap, but they are also very limiting because it can only see. So you see, it shoots the laser in just one direction like this. So it will only know if the objects are at this height. So that's why it's quite limiting. But it does a fairly good job if your environment is neat and clean, like the corridors in our university, for instance, or in hospital environment, or in offices where there are less obstacles, less chairs, and more neat and clean corridors, for example. So the environment here was, we used is embedded system which was based on an FPGA. So we implemented everything there, and most of the so the only sensor here is the LiDAR, and we are using some odometry values from the wheels that are inside this robot. So this is one quick scenario of this. So you see, the robot is moving in a corridor, and ultimately when it makes multiple passes, it is more and more confident about the shape of the corridor. So eventually now it has made a map of the corridor. This is another view of a more complicated corridor. So this is one of the buildings in our university in one floor. And so you see robot is autonomously moving around, and you see this this was a break here, and that was the door that we opened for the robot. So earlier it was not there, so robot thought that it was a wall, but we opened this door for it, and now it was able to move through that. But now after making certain passes, now we have the map of the building. So this is useful in certain cases where we want to send a robot to an unknown environment, and it will just move around and make a good estimate of what the inside of the building looks like. But this is 2D LiDAR. If we had used a 3D LiDAR, then the map would have been perfect. But as I mentioned, 3D LiDAR is pretty expensive, totally out of the budget in universities. But fortunately, we could extend this using the video-based lamps. So in video, we could do the video place recognition, and then we could do a similar job in a much better way. So that's our next target, inshallah, that we'll do with respect to this project. The second case study, this is actually not a very intelligent robot. This was done by our ECE students as a final year project. So we built this boat, you could say, but strictly speaking, the technical name is the surface vehicle. And this was autonomous because it had a autopilot on it. And we built it using the locally available resources, except for these parts here, which we bought, which we had to import. But anyway, these are the fishing trolley motors. So they are used. These motors are used by the by people who fish in the sea. So they would want a quieter motor so that the fish don't run away. So we use this, we hooked this up with the custom made structure here, and then we connected it with another very famous autopilot, which is the RD pilot. So the thing is that at the start of the project, I personally was quite nervous because we could not find any example online where people hooked up these fishing motors with the Pix Hawk, and we had to install them on our own custom made structure, which was done by our aeronautical department. So a lot of things were there. They should have worked in theory, but we did not have anything in practice. But alhamdulillah, we were on the very first attempt on, we took this to the sea, and we had hooked everything up on, although we were confident that this would work, but we had never tested it. But alhamdulillah, it made a very good show. And you see this board, this is from Coast Guard. So the Coast Guard came to actually witness this, and this did a very good job of navigating in the sea around our faculty of Marine College. This is where we are actually assigning the paths. So we did not do any intelligence here with respect to AI or any other thing like that. It was just a demonstration of the autonomous control, that if we tell the system to go from A to B, so is it doing that or not? So this was, you could say, more of a using off-the-shelf components and integrating everything up to deliver a system. And the results were alhamdulillah very good. I was happy with that. But strictly speaking, we did not go into the details of it. We did not make all the parts ourselves. We just integrated them. This was another project done some 2 years ago, autonomous mini cars. So these students, they took a children toy car and they converted it into a mini autonomous car. So they built this around Raspberry Pi, and it had LiDAR and GPS and everything, and then it had also some custom machine learning components there. So for example, here you could see it is detecting the speed signs. So it detects the speed sign, and it then accordingly it changes its speeds according to that. And it has obstacle avoidance using LiDAR. Again, this is a 2D LiDAR, so the same LiDAR that I had showed you earlier. It is quite limiting, but it can do some basic obstacle avoidance. But since we also have the camera there, which is doing this this object detection here. So eventually we could also do the segmentation like I showed you before. So segmentation will segment this road and the cars separately, and then we could do some more autonomous car features there. And it had a few ROS nodes in it. So this is, strictly speaking, again, not a very robotics related thing, but it was supposed to work on a robot. So in the AI Neom Challenge 2020, we participated as a KAU engineering team, and alhamdulillah, we came third here. So this was about a telepresence robot. So you have a robot at a remote location, and you control it remotely over the internet through VR goggles, and that VR goggle is powered by a smartphone app. So a lot of AI component is there. So AI is doing this autonomous operation plus detection of various places there, and it is transmitting the video, and it can take some form of control from there as well. And based on the head-mounted gear there, so it can sense, there is a smartphone there, so the smartphone can sense the direction of the motor. So those motors will change the head of the robot accordingly. So you could have a more immersive feeling. So it will look like that, as if you are actually visiting that place instead of that robot. So this robot used the Jetson Nano, not a very big system, but it was able to handle the minimal AI tasks that we had given it. And on the other hand, we had, of course, a simple smartphone. So this, you could say, this comes under the visual place recognition task that we had discussed earlier on, that your AI could see, you could distinguish, or it could check where they are. So we had some, we had selected some famous places from in Saudi Arabia, so it could do this visual place recognition. It could tell what you are looking at exactly right now. So in terms of the hardware platforms, you could do a lot of, you have a lot of variety these days. So you could start with very simple systems like an Arduino, for example. And on an Arduino, although you are limited, but there is a new branch of machine learning coming up, and that is TinyML. So you could port small machine learning algorithms there as well. But of course, that is quite limiting, and you would quickly want to move on to bigger systems like Raspberry Pi or Jetson Nano, where you could do some image processing. And this ESP32 cam, that's a RISC device. Sorry, this is not a RISC device. This is an ESP32 device, and this is the RISC device. So this can do vision processing plus some machine learning part could also be ported. But ESP32 cam, I'm not sure if you could port some machine learning there, but you could do some of your own computer vision tasks there. So a lot of interesting hardware is already available very cheaply, and you could experiment a lot if you wish. So essentially, if you are looking to build a robot, you should be prepared for a lot of things. So I have not included the power electronics and other stuff there, because I'm assuming that that's the understood part. There will be a lot of mechanical work as well, power electronics, batteries, and wiring and such. But other than that, if you want to make your robot interesting, be prepared for a lot of programming, doing a lot of mathematics, and a lot of algorithm design. But that's of course obvious, because engineering, if you're not tired, you're not doing it right. So that's it. If you have any questions now, I'm open for that.
Thank you so much, Dr. Muhammad, for this opportunity. I'm sure that everyone here, including me, gained a lot of knowledge and a lot of information on the robots. So now we will open the chat for any questions.
if anyone want to maybe direct their questions later on, so you could please use my email for that as well.
الله يعطيكم العافية جميعا على الحضور. هذا إيميل الدكتور محمد، في حال عندكم استفسار أو أي سؤال تقدروا تفضلوا، واللي عنده السؤال يبغى يطرحه يقول الآن، يفضل يكون باللغة الإنجليزية عشان الدكتور محمد يقدر يجاوب عليه. ثواني بإذن الله الآن ونرسل الرابط. Yeah, so I think there are no further questions.
All right,
thank you, Doctor, for this webinar, and we're glad to have you here with us. Thank you.
Okay.